In this video, we will explore classic synchronization problems, which are fundamental concurrency challenges in operating systems. We will cover the producer-consumer problem, the readers-writers problem, and the dining philosopher's problem. Each of these problems illustrates common issues in concurrent programming and provides a framework for understanding synchronization techniques. The producer-consumer problem is a classic synchronization challenge where multiple processes share a fixed-size buffer. Producers generate data and place it into the buffer, while consumers remove data from the buffer for processing. The buffer is a critical resource that requires careful synchronization to prevent issues such as buffer overflow, when the producer tries to add data to a full buffer, and buffer underflow, when the consumer tries to remove data from an empty buffer. To summarize, producers create data and place it in the buffer, consumers remove data from the buffer. The buffer is a critical resource requiring synchronization, and we must prevent buffer overflow and underflow. The diagram illustrates this setup, showing producers adding items to the buffer and consumers removing them. Here is an implementation of the producer-consumer problem using semaphores. In the producer process, the producer first produces an item, then waits on the empty semaphore, which indicates the availability of empty slots in the buffer. It also waits on the mutex semaphore to ensure exclusive access to the buffer. Once both conditions are met, the producer adds the item to the buffer, signals the mutex to release the lock, and signals the full semaphore to indicate that a slot has been filled. On the consumer side, the consumer waits on the full semaphore, indicating that there is data in the buffer, and then waits on the mutex semaphore to gain exclusive access. After acquiring both, it removes an item from the buffer, signals the mutex, and signals the empty semaphore. We use three semaphores here: mutex, which is a binary semaphore for mutual exclusion; empty, which is a counting semaphore that tracks empty slots; and full, which is another counting semaphore to keep track of filled slots. Here we have a complete implementation of the bounded buffer solution with initialization. We define a shared buffer of a fixed size, such as 10, along with in and out indices to manage the buffer as a circular queue. Semaphores are initialized as follows. The mutex is initialized to 1, ensuring mutual exclusion. The empty semaphore is initialized to the buffer size, indicating all slots are initially empty. The full semaphore is initialized to 0, as no slots are initially filled. This implementation uses a circular buffer, employing modulo arithmetic to wrap around the buffer indices. Careful ordering of wait operations helps in deadlock prevention. The fixed buffer size prevents overflow and memory issues. The readers-writers problem is a synchronization challenge where multiple processes access a shared resource with different access patterns. Readers only read the shared resource and can do so simultaneously, while writers require exclusive access to modify the resource. No reader should wait unless a writer is accessing the resource, and once a writer is ready, it should perform its write as soon as possible. There are two common variants of this problem. In the first readers-writers problem, readers have priority, while in the second readers-writers problem, writers have priority. The diagram illustrates readers and writers accessing the shared resource. This is the first readers-writers solution, in which readers have priority over writers. We use three shared variables: mutex, which controls access to the read count; write, which controls writing access; and read count, which keeps track of the number of readers. In the reader process, a reader first waits on the mutex to access the read count. It increments the read count, and if it is the first reader, it waits on the write semaphore to block writers. It then signals the mutex. After reading, the reader waits on the mutex again, decrements the read count, and if it is the last reader, signals the write semaphore to allow writers. Finally signals the mutex. The writer process is simpler. It waits on the write semaphore for exclusive access, performs writing, and then signals the write semaphore to release the lock. In this solution, the key point is that the first reader acquires the write lock, and the last reader releases it, allowing multiple readers simultaneous access while ensuring exclusive access for writers. This is the second readers-writers solution, in which writers have priority over readers. This implementation uses several shared variables including mutex for readers, mutex for writers, write-to-control writing access, read-to-control reading access, the read count and the write count. Let us compare this solution to the first readers-writers solution. In the first readers-writers problem, readers have priority over writers, writers may starve if readers continuously arrive. It features a simple implementation with 2 semaphores and it is good for read-heavy workloads. In the second readers-writers problem, writers have priority over readers, readers may starve if writers continuously arrive. It is a more complex implementation with additional semaphores, and it is good for write-heavy workloads where data consistency is critical. The Dining Philosopher's Problem is a classic synchronization challenge that illustrates issues in resource allocation and deadlock avoidance. 5 philosophers sit at a round table with 5 forks. Each philosopher alternates between thinking and eating. A philosopher needs 2 forks, left and right, to eat, and forks are shared resources between adjacent philosophers. The key challenges include deadlock, which can occur if all philosophers pick up their left fork simultaneously, starvation, where some philosophers may never get to eat, and resource utilization, aiming to maximize concurrent eating. The diagram illustrates the philosophers around the table with shared forks. This slide presents a semaphore-based implementation to solve the dining philosopher's problem and prevent deadlock. Each fork is represented by a semaphore initialized to 1, indicating that all forks are initially available. A mutex semaphore is used for mutual exclusion to protect the critical section of picking up forks. In the philosopher process, a philosopher first thinks, then enters the critical section by waiting on the mutex, picks up the left and right forks by waiting on their respective semaphores, and signals the mutex to exit the critical section. After eating, the philosopher puts down both forks by signaling their semaphores. There are alternative solutions to this problem. In the resource hierarchy solution, forks are numbered and always picked up in ascending order. In the arbitrator solution, a mutex ensures only one philosopher can pick up forks at a time. And in the Chandrai-Mishra solution, forks are either clean or dirty, and philosophers request forks from neighbors. In summary, the producer-consumer problem models producer-consumer workflows, using a bounded buffer as a shared resource to prevent overflow and underflow, with applications in print spoolers, web servers, and multimedia processing. The readers-writers problem models database access patterns, allowing multiple readers or one writer, with variants prioritizing readers or writers, and applications in databases, file systems, and shared caches. The Dining Philosopher's Problem models resource allocation challenges, illustrating deadlock and starvation, with multiple solutions offering different trade-offs, and applications in resource allocation for distributed systems. These classic problems provide frameworks for understanding and solving real-world synchronization challenges in operating systems and concurrent programming. The solutions demonstrate techniques for managing shared resources safely and efficiently. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.